Dr. Dinagaran, you can share your slide by the time, all
Yes,
of
sir.
us
I will do that.
switch on our video and
Yeah.
our coordinators and we can take a snapshot of this for some
Yes,
record
sir.
purpose.
Yeah. Yes, sir. I will launch my presentation. Yes, sir. I have launched my presentation, sir.
Yes, it is visible for us too.
Yeah, it's visible. Yes. Oh, yeah, that's good. Thanks.
HOD sir, share adala sir. Yes, sir. Yes, sir.
That's clearly see.
Oh, that's good.
Dr. CSK sir. Dr. CSK. Hello. I think some mic problem, sir, for him. Hello, Dr. CSK. Am I audible for you, Dr. CSK? Hello, Mr. Kumar Swami, sir.
Yes, sir. Yes, sir. Yes, sir.
I think for others it is fine. He typed me some problem with his hand, it seems, for him.
Yes, sir.
He said he is not able to receive our audio. He has left the meeting also.
Shall I start, sir?
I will request HOD, sir. Shall we start, sir, then?
Yeah, no issues. You can start, sir. Already started the time. You can start.
Yes, sir. Now I am audible, sir.
Oh, yes, sir. Yes,
Yes,
now you are audible.
very well.
Yes, you
Yes,
can.
sir. Yes, sir. Good evening, one and all. I request all participants to mute your audio and video. I invite Dr. R. Ramesh, Professor and coordinator of this webinar, to welcome the gathering.
Thank you, Dr. Sandamarai. Good evening to everyone. Respected head of the department and convener of this event, Dr. Ramesh Babu, sir. Speakers of today's section, Dr. Dinagaran Sambar, project leader, research and development, Tata Steels, Swansea, United Kingdom. Senior professors, faculty members from our college and department, and dear participants from various other institutions, industries, and research organizations. I'm very happy to welcome you all for this international webinar on hydrogen embrittlement degradation of engineering metals, organized by Department of Mechanical Engineering, Sri Venkateswara College of Engineering, Sri Perumbudur. The webinar session is aimed at exploring the challenging attributes in failure analysis in design of many engineering methods for meeting out the real-time engineering application. We hope the program will be very much useful for the faculty members, researchers, industry practitioners, students, and will give you a platform for knowledge sharing and future challenges involved. We have around 490 participants registered for this webinar, and I am proudly would like to say that many participants registered from the other states of India and even some from other country like Indonesia, Iraq, Saudi Arabia, Ethiopia, Oman, and Turkey. On behalf of the Department of Mechanical Engineering, SVCE, I once again welcome you all for this international webinar session. Thank you all.
Thank you, sir. Now I invite Dr. S. Ramesh Babu, Head of the Department Mechanical Engineering and convener of this webinar, to give his presidential address. Welcome, sir.
Thank you. Respected expert member Dr. Janagaran Sambar, project leader, fracture and cutting metallurgist, research and development, Tata Steel, Swansea, United Kingdom. Respected coordinators Dr. R. Ramesh, Dr. C. Sandamari Kandan, Mr. G. Tirubagaran, Mr. J. Sivaram Pandian, faculty members from Mechanical Engineering Department of SVCE, faculty members from other departments of Sri Venkateswara College of Engineering, faculty members from other institutions, research scholars, student participants, participants from industries, warm welcome and good evening. And it's good to hear from our coordinator, Dr. Ramesh, that the participants even from other countries. It shows the importance of the topic, that is the hydrogen embrittlement, degradation of engineering materials. Now, with the kind permission of the coordinator, I want to share my screen with respect to the small presentation of our department regarding the facilities, because there might be a student from other colleges who might want to know about our department and the facilities available, so that they can come forward to do some collaborative work. There might be a faculty members in other department or other colleges and all who can come forward to do collaborative work with the department. So, expert member, I want to share my screen.
Yep. Okay. I will just.
Thank you, sir.
Yep.
Nagar sir, you can also mute presently. Yeah, kind of.
So thanks to the coordinators for organizing this webinar on hydrogen embrittlement, and also thanks to the speaker for spending his valuable time in gathering his experience and also his knowledge to the participants. Now coming to the department, under the shadow of Mechanical Engineering Department, we have one UG program and two PG program. BE Mechanical Engineering is a PG program being offered by Mechanical Engineering Department, and it was established in the year 1985. And this BE Mechanical Engineering program is accredited since 1998. And those who are in the academic institution, they might be knowing the accreditation, that is the importance of accreditation. And very recently, it has come to the practice such a way that those who want to pursue their masters in abroad, or they want to pursue their the job in the abroad and all. Okay, the companies ensure that whether the degree is accredited by National Board of Accreditation. And our intake is 120, and our curriculum focuses toward automation and additive manufacturing. Coming to the PG courses, we offer two courses. One is ME in Mechatronics and ME in Industrial Automation and Robotics. This ME in Mechatronics was established in the year 2013, and recognizing the need of the today's industrial scenario, okay, we started the new PG program, that is ME in Industrial Automation and Robotics. And if you see the curriculum focus towards the low-cost automation, and in the case of ME Industrial Automation, it focuses towards Industry 4.0. And since our degree, that is a bachelor's degree, is NB accredited, our BE degree is globally accepted, and this department is recognized as a research center by Anna University because of our faculty strength. One unique feature is that we follow choice-based credit system in our curriculum. It means that the student, apart from the professional course, what they can do, depending upon the requirement, they can select some online courses, they can select some department courses from other subjects, okay, depending upon the need. Okay, this is the practice which we have incorporated in the new curriculum. As I told, the main strength is a faculty strength. If you see this, nearly 61% of the total strength of faculty or doctorates, and 32 are pursuing the doctorate. In another 2 or 3 years, nearly 93% will be a doctorate in a department, and only two more faculty, that is 7% of total strength, are yet to start the career in the pursue the doctorates. And what is the uniqueness? Okay, there might be some aspiring candidates. Okay, that is who will be about to complete the bachelor's degree right now, and that is considered the present scenario. They might be having the willingness to join for a PG. So, what is the uniqueness of pursuing PG at SVCE? Okay, it's a 35 years old department, and as I already told you that 60% of faculty or with doctorates. And our department is recognized as a research center by Anna University. The curriculum for ME mechatronics and ME industrial automation robotics are completely designed by the industrial experts and leading academicians. And we have mechatronics, automation, modeling and simulation, artificial intelligence, embedded PLC laboratories, which are essential for the today's industry requirement. And if you see the syllabus for ME industrial automation, it focuses towards Industry 4.0 curriculum. And we have a management scholarship for tuition fee and books, which will not be given by many of the colleges for PG students. Okay, here even for a PG, we give management scholarship for tuition fee and books, and we have a AICT scholarship at the rate of 12,400 per month for a valid GATE score. Another important thing is that we also have an intramural PG merit scholarship at the rate of rupees 5,000 per month for 20 months. Okay, based on certain criteria. Okay, that is six students in out of 18 students will be eligible for availing this scholarship. And we also have intramural PG research grant to carry out innovative research projects in the fourth semester. We do sponsor our students to attend the conferences in India and abroad. So these are the unique features which are available for pursuing the postgraduate degree at SVC. To inculcate the leadership quality and also to have a very good professional development among the students, we have Society of Mechanical Engineers, the Quality Management Center, Indian Institute of Building. So under the various professional society, we do organize various activities and also conduct various programs which the student participate and also bring laurels to our department. The photo dissipates some of the activities being carried out by the students by taking part in the Baja competition, by taking part in the aero modeling competition, and also regularly we do conduct the program related to the Green Belt and Six Sigma training under the Quality Management Center. Coming to the infrastructure, I showed only the basic infrastructure. If you see our infrastructure, the students might have a real feeling of being in a small industry, and also our equipments are normally we never procure what is that training sort of models and all. Okay, we go for only the industrial type of machine tools and all. We have a real boiler. We have a vertical machining sensor, CNC turning center, coordinate measuring machine, and also we develop our own friction stir welding machine. We have a laser engraving. We have a cold metal transfer. Right now, which can be used for wire arc additive manufacturing process. And also, we have purchased one camera with a high resolution camera, which can take a photograph inside an engine, what is happening inside, and so that depending upon the injection pressure, so how will be the emission characteristics. So these are, and also we have a pin on disk. So these are all the very few facilities which I have shown. Apart from that, we do have very good testing facilities also. And coming to the placement particular details and all, okay, how we are able to consistently place our students, that is eligible students, okay, that is our we meet a target of 90%. And for our department, the mechanical engineering department, we have a placement in software and also the core-based companies. One advantage for the student is that if they have been selected in a software-based company, they also can take a job in core company also. That is the main feature where many colleges never allow this kind of that is a dual offers and all. Here in mechanical department, if the person got selected in a core or software-based company, he can also seek for a core companies and many students have a dual offers also. So this is about the small presentation about our department. Any student want to have more detail about our department and the institution they do can visit our college and also our department webpage. And coming to the today topic, that is hydrogen embrittlement, degradation of engineering metals. It's really a wonderful topic, and those who want to pursue research in this topic, I think this topic will be very, very useful for us. And so far, I came to know about the corrosion, degradation, or oxidation gradation. Okay, so out of curiosity, I have gone through, I googled, okay, what is my hydrogen embrittlement and all. There's nothing but the absorption of hydrogen. I'm not going to talk because our expert is there, and he will be sharing more his experience and all. And I came to know that it's a very, very worst condition compared to oxidation and what is that, the other other degrading properties and all. I hope that today's session will be very much interesting, and dear participants, okay, those are about to pursue the research. I think this topic will be useful for you. With this small presentation or this small note, I once again say thanks to our thank and also welcome our speaker, Dr. Dinagaran Sambat, and also wish a good luck for all the participants. Thank you.
Thank you, sir. I'm audible, sir?
Yes.
Yes, sir. Audible, sir.
Dear participants, please mute your video. Some of you showing your video, please mute your video. Satish Babu, sir, mute your video. Now I request Sivarama Pandian, Assistant Professor, Mechanical Engineering, and one of the coordinator to introduce our international guest speaker of this session. Welcome, sir.
Yes, sir. Thank you, Sandamagan, sir. Good evening to all of you. I am very happy to introduce today's resource person, Dr. Tinagaran Sambat. Dr. Tinagaran Sambat is currently working as a project leader, fracture and fatigue metallurgist, research and development, Tata Steels, Swansea, United Kingdom. He is involved in the many real-time research projects related to development of infrastructure and engineering steel products for high-value markets. As a researcher, he is also on affiliate in Swansea University, United Kingdom, and conducts different collaborative research activities with Steel and Metal Institute, a division of Swansea University, United Kingdom. He did his bachelor's degree in mechanical engineering from Institute of Road and Transport Technology, E-Road. He received his master's and PhD degree in machine design from Indian Institute of Technology, Madras, Chennai. He did his postdoctoral research at the University of Manchester, United Kingdom in the year 2015. The postdoctorate was on hydrogen embrittlement of nickel alloys funded by the BP International Center for Advanced Materials. He has published over 21 research articles in peer-reviewed journals. He has served as a reviewer for a handful of reputed international journals. His research interests include fracture and fatigue, corrosion, fatigue, crack growth behavior, processing structure property relations, material characterizations using sophisticated analytical instruments, high resolution digital image correlation and quantitative failure analysis methods using scanning electron microscopy and X-ray computer topography. I once again feel happy to have introduced Dr. Dinagaran Sambat, today's eminent speaker. I hand over the session and invite you, sir, to deliver the talk. Thank you, sir.
Thank you,
Yes.
Sivaraman Pandian, sir.
Yes, sir.
It's a great pleasure to join this webinar. Thanks for the introduction. I will try to launch my presentation. So everyone can see the slide now, are you?
Yes, sir. We are receiving.
Okay, that's good. Okay. Yeah. Thank you very much. It's a great pleasure to be here in this forum with you all. Yeah. Thank you very much for inviting me to this talk. Yeah. Okay. So I'm going to give a bit of a background about where I work. So as Mr. Sivarama Pandian introduced me, I work in one of the R&D centers of Tata Steel, Europe. They have got three R&D centers across Europe and UK. So I belong to Swansea Center. So here we do all of the fracture and fatigue experiments, including environment-assisted cracking. And they have got access to several aggressive gases to simulate blast furnace. So that's the blast furnace is the structure that we use to produce steel. So yeah, to simulate certain things of blast furnace, and also for product performance evaluation. So so we collaborate with Steel and Metals Institute of the Swansea University. So we also based within the university, so we can readily we can have an effective collaboration with the professors and also students. So yeah, and one highlight I wanted to say, which I heard in the recent news. So Tata Steel Europe makes a premium product. It's a structural tube steel called Celsius. It's our premium brand. So the news is the famous Barcelona football stadium in Spain. They are going to renovate using that high quality, high strength tubes. So with that note, I'm going to begin my presentation. So my talk is on hydrogen embrittlement degradation of engineering metals. So yeah, there is no better time than now to pursue this research on materials for hydrogen. Why? Because there are two driving forces. One is several of the industries. In a couple of minutes, we're going to see that industries. So they experience hydrogen related failures in wide range of materials. In particular, if you look at oil and gas, they use exotic materials like nickel alloys in oil and gas production systems. So what happens is, when the oil price was good, they were able to, if there is any failure in the oil well, they can just abandon and go and drill very next to the failed well, and then they don't mind about losing the well. But now it has become the oil, as you know, oil prices are become highly competitive. So they are going for, they're trying to reduce their operational costs. They are trying to reduce their failures and extend the life. So that is where that the driving force comes for fine-tuning these materials for hydrogen services. And also, secondly, these days, zero emission is the new normal. So several countries have different targets. So hydrogen fueled vehicles are very important, but yeah, to make it affordable, so that the transition is quick. So that is where the alternative materials for hydrogen storage tanks is also emerging research area. So in my today's talk, I'm going to divide this talk into two parts. One is I'm going to give an overview of hydrogen embrittlement. So looking at failures, factors affecting hydrogen embrittlement, mechanism, testing, and then also we'll talk about mitigation strategies, and then I'm also going to touch upon some challenges we have. And secondly, I'm going to present result which I have done when I was there in University of Manchester. So that's one interesting area where we could I have developed quantitative fractography along with my colleagues in the university. So I will go through that results as well. So what is hydrogen embrittlement? So that's a very
sorry to disturb you, sir. Sorry to disturb you. Screen is not visible, sir.
Really?
Yes, sir.
Okay.
It's coming, no, sir? Hello?
Hello, sir.
I think it dropped, I think.
Okay. Can you re-share it, sir?
Yes, sir. I'm going to share it now. Yeah. Yes, sir. Yeah. So is my screen up again?
Yes.
Yes.
It has
Okay.
come.
Thank you.
Yes, it has come. Yes, sir.
Okay. Thank you. So what is hydrogen embrittlement? It's a sudden fracture of metals and alloys due to the presence of hydrogen in the metal lattice. So what I mean by lattice? It's the crystal structure, the atoms arrangement. So that is, we have a lot of gaps in the lattice. As you know, hydrogen is the smallest atom, so which can just pass through all these gaps. So that is how it diffuses through the lattice. So it goes to, it stays in the matrix, that is the main metallic element in the alloy, or interfaces between any interface in the microstructure, or precipitates, and also defects like point defect, line, and all forms of defects. So what happens is sudden fracture occurs under both sustained and fatigue loading. What I mean by sustained is constant load or monotonic loading, and then fatigue load is cyclic loading. So what happens to the material is we can see that it macroscopically it shows brittle fracture features, which the material normally behave like a ductile material. So that's the problem. So we don't see any hint before it fractures. So many, it's an interdisciplinary effort made by several groups, several communities, mechanical, metallurgical, electrochemical, and corrosion. So all these communities work together to better understand and produce better material. So infrastructures that face hydrogen-related failures are offshore. So you can see this massive structure. They are in marine environment, and they, one way or the other, hydrogen enters into the metal. Of course, they have protective coating and several of the stuff, but as aging structure, just 1 weak link is sufficient enough. And also there are several scenarios under which hydrogen enters into these structures. And for example, in chemical processing, they handle very aggressive fluids. So they also, choose exotic materials to avoid failures, and also extend the operation of their assets. And here I'm going to dwell some time on this. This is called wellhead, which is actually the structure that sits on the mouth of the well. Basically, you can see that it's a large structure. You can, in comparison to the people around them, it is holding the entire tube string, which is running down into the oil well, which is, it's going to be very heavy. And also, under production, the fluids will come out of the well at high pressure and temperature. So this section will experience very high stress as well as very aggressive environment. So basically, they need to use materials or alloys called corrosion resistant alloy. So those are the ones which can sustain this kind of demanding environment. And you can see this long distance pipelines. They are also exposed to hydrogen environment. Other infrastructures such as nuclear power plants, for example, they also have several of these failure mechanisms. One example is hydrate cracking, which is also because of hydrogen getting into the metal. So what happens is in nuclear fuel rods, they use zirconium alloy. When that's a hexagonal close packed crystal, so that alloy forms hydrates with hydrogen. So that is a brittle phase, and it starts to crack, and it is very, very dangerous. We don't want. So people work on zirconium alloy to prevent any failure. Yeah. And as I told about hydrogen fueled vehicles, they are actually emerging research area. So they are looking for alternatives for stainless steel, which is at the moment resistant enough to postpone fracture. So what are the hydrogen damage we see? More broadly, there are about 3 types. So hydrogen blistering, which occurs in low strength alloys. That means having low yield strength. So in the presence of high hydrogen concentration, so they enter. So these are present in an electrolyte. So basically, the hydrogen is generated through electrochemical process, and the hydrogen, it splits into single H, that is called nascent hydrogen or atomic hydrogen. So that's the one in the form of also called this adsorbed hydrogen. So that enters into the metal. So it will not enter as H2, it will only enter as H, and it diffuses through the matrix, and whenever it hits some of the interfaces or voids, it goes there, accumulates hydrogen there, and then due to thermodynamics, they recombine and form hydrogen gas. So what happens is these are very low strength alloys. The hydrogen accumulates and it creates a huge pressure, which exceeds the yield strength of the material, and at that point it leads to bulging or blistering. So blistering later on will become a crack or some crack, and then become a catastrophic failure. And today's topic, hydrogen embrittlement, which happens in high strength alloys at low concentration. So in this one, we need external stress to have this failure to happen, and we are going to see that in detail. In case of hydrogen embrittlement, hydrogen blistering, we don't need any external stress to effect this failure. And in hydrate cracking, as I told in zirconium alloy, here we are seeing a phase map. Phase map, it will show, for example, this material has got zirconium hydride oxide, zirconium oxide, and pure zirconium. So the blue are all zirconium, and red color all zirconium hydroxide. So the red color region are very brittle compared to other the blue color, and the green one is the oxide, which is at the outer surface. So they are very brittle, that they crack in the absence of stress, external stress, and in the presence of external stress, it's going to be still worse. So these are very critical mechanical failures which one should consider when designing. Of course, they are very critical. Nuclear industries are very critical about it. And I'm going to talk about the tubing hanger. So we saw that well head, which is fixed at the mouth of the well, and underneath we have a long string of tube, and tube hanger is the one which is holding the entire section, which runs in meters. So what they do is the silver color tube is actually is duplex stainless steel, and it cannot hold that heavy stress coming from holding the entire structure.
Dr.
So they
Dinagar,
use,
sorry to interrupt. A little louder voice, because I think your mic may be a little away, it seems. Little louder
all
voice.
right, okay,
Now it's comfortable.
right.
Yeah. Thank you.
Oh,
Kind
okay,
of.
brilliant. Thanks, sir. Thanks. Okay, I will speak louder. Yeah. So here we are seeing the copper plated nickel alloy, nickel 725, which is a very expensive alloy compared to duplex, but they use it because of that high stress and aggressive environment to withstand that. So what happens is, in this case, this failed within a short period of time. Actually, it is like very less than 5% of its lifetime. So when they looked at this is the failed outer ring, which is that copper coated nickel 725, and they examined this fracture surface and found that it showed intergranular cracking. That means crack grows through the grain boundaries of the microstructure. So and then they did several additional tests to find that it is only because of hydrogen from electroplating this section of this component, and also the hydrogen generated from the fluids that it was handling. So this is very critical. This is very expensive. And what happened is, as I told, now they can't abandon the well and drill very next to it. They have to sort this out. They pull this out to understand this way. They no longer tolerate failures like this. So that's the one key driving force to pursue this research, and then to come up with hydrogen embrittlement resistant alloys. And here I'm showing another interesting graph where we are seeing plane strain fracture toughness, which is actually measured in stress intensity factor in the units MPa root square meter. So what this parameter means is it's the ability of the material to resist unstable cracking. So while once it reaches this kind of stress intensity, it will fracture until it becomes two pieces. So what is this is actually it defines the stress field ahead of a crack tip. So the crack tip stresses are very different from uniform stress. So that is the stress concentration or intensity is defined by the stress field ahead of the crack tip is defined by stress intensity factor, and the stress intensity factor at which the specimen, the material undergoes unstable cracking is called fracture toughness. So what I'm showing here is on the x-axis we have tensile yield strength, which is running between 800 and 2400. Metallurgists and scientists worked hard to get the combination of high strength and toughness, which is usually mutually exclusive. So we can't achieve both at the same time, but with hard work they got this. And in the presence of hydrogen, for example, in this case 600 megapascal and 200 MPa root meter, and in the presence of hydrogen it just drops down to only like 5 to 25% of the fracture toughness in air. In hydrogen it becomes very the unstable cracking happens very early with small driving force. So what we see in the fracture surface, so in air we see dimple features like this arising from wide coalescence phenomenon. And in hydrogen, the crack runs through grain boundary, and we can see that grains itself with facets, and you're seeing the surface of the boundaries. And this is very brittle compared to this. So that means the ductile fracture will be slow and gradual, but brittle fracture like this, intragranular fracture, will be very sudden. And yeah, it's without any hint. In anodic corrosion, we'll see some oxidation on the surface, but with hydrogen, it just keeps bubbling. I will show one picture. It'll be shiny as installed, but suddenly it will just go off. So factors affecting, so we need all three components: hydrogen environment, material properties. I mean here the high strength alloys are very, the high strength is very deleterious. And also if we have phases in the grain boundary which is also detrimental, it will promote grain boundary cracking, intragranular cracking. And mechanical stress, again, it's very important, either sustained or fatigue loading. And hydrogen environment, it could be electrochemical based or gaseous based. So all of its environmental parameters play a role in the susceptibility of a material. So what are the hydrogen sources? One is, the material will get hydrogen from manufacturing process when they are made. Such example, casting, welding, acid prickling for cleaning the surface, electroplating to reduce corrosion or to prevent corrosion. So these are like one-time ingress of hydrogen into the material. So this is okay, because there are some methods to overcome this. And in-service exposure is very complicated because hydrogen is there throughout the life of the material in service. So a few examples are cathodic protection for corrosion of the material. Actually, if it is, sometimes it will hit over potential, which leads to hydrogen generation in excess. And some people say even in air, due to moisture, we'll have hydrogen into the material, but it depends on, once it reaches some critical concentration, it'll also be detrimental. And as I told, gaseous hydrogen environment. So what it really does, I think we covered this a bit. Atomic hydrogen occupies lattice or trap sites in the microstructure. So lattice, of course, this is the crystal structure, and I said about the gaps in the structure through which hydrogen diffuses. What is trap site? Actually, there are some regions in some microstructural features have high binding energy, which will hold the hydrogen better than the lattice. So before that, hydrogen diffusivity, which is actually in centimeters square per second. The diffusivity is the rate at which the hydrogen passes through the material. So in BCC, it is very high, body-centered crystal, and in HCP, compared to HCP. In case of hydrogen solubility, that means how much hydrogen it can hold in the matrix. So in HCP, it is very high. I think that in HCP, like zirconium, titanium, some forms of titanium, it forms hydrate, so which is also very problematic. But most of the today we are going to look at only BCC and FCC materials, like BCC steels and FCC nickel alloys, which is austenitic. So traps have greater binding energy than lattice sites. For example, some second phase particles which will hold more, which will hold hydrogen. That means it will accumulate more hydrogen in the location, and we'll see that some mechanisms which will tend to weaken the location because of the trap sites, and also they are sometimes beneficial. So that's the trick. Yeah, and because of this trapping phenomenon, hydrogen transport doesn't follow fixed law of diffusion. So yeah, so we can't use that. There are so many models, starting from Oriani model. So they account for trapping as well. So to understand, how the hydrogen transports. And also the cracks, so stress gradients in the material, stress rises also attract hydrogen, thereby accumulate lots and lots of hydrogen. That means at the crack tip, hydrogen accumulates a lot. So we are going to look at some models, models. They actually explain the mechanism. So this is very early model, hydrogen enhanced decohesion. So what happens is, in the presence of hydrogen, it lowers the cohesive strength of the atomic bonds. So what happens is it just unzips and initiate a crack, which is atomic lattice distance sharp. So that is that means it will have a very high stress intensity at this location, and it just unzips all along. So that is why they call it as decohesion. It just separates. And in case of crack, as I told, the hydrogen doesn't accumulate at the very tip of the crack, but some distance ahead of the crack. So they call, because the hydrostatic state of stress is maximum at that point. That is where hydrogen, goes and sits there, because of that expansion there, for more hydrogen to sit there. And in case of some obstacles, some second phase particles, when dislocations takes creates stress rise at there, stress concentration or stress intensity. So hydrogen goes there, and again, this is the second phase atoms and matrix atoms, and because of the hydrogen, it just unzips, leads to a crack. So this is the very early model. This is, this is not experimentally proved, because this as one has to see at the atomic scale. Only simulations are there. Hydrogen enhanced local plasticity, which is very recent one, but this is very comprehensive mechanism, which tries to explain several of the observed phenomenon in this failure. So what it says is, hydrogen, in the presence of hydrogen, dislocation density increases and velocity also increases. So what is dislocation? It's a line defect, which is actually the basic unit of plasticity. That means it will create permanent strain in the lattice. So yeah, once there are several of this happening, and that is when we are seeing that yielding happens and further hardening depending on the material type. So if that dislocation density and velocity increases, then that means it is actually more plasticity is promoted in the presence of hydrogen, leading to lowering of yield strength locally. So this is like void formation, as we saw in the case of in air, but the size is very small because the hydrogen actually localizes. See, in the presence of crack, we normally have a big plastic zone because of very high stress, and the material, once it reaches the yield point, it creates a plastic zone. And in the presence of hydrogen, that zone is very small, and inside that we still create voids, because at the intersections of line defects, that is dislocations. So they are actually, even though they appear like a flat surface, but they have, at micro and nano scale, they have voids similar to what we see in in air. So that's actually the very popular model to describe most of the material behavior. And because there are several ones, but for this presentation, I took the most important three. Adsorption-induced dislocation emission. So this one, once the hydrogen enters the surface, it creates a dislocation and helps to move the dislocation, which means we get this localized shearing. and at the intersection we know it forms voids that leads to cracking, continuous cracking. So this is adsorption induced dislocation emission, as the name says, and it explains this herringbone fracture pattern very much, because it shows this crystallographic pattern. So this is also a very important model, so most often what will happen is all three models will go will be will be seen in most of the materials one way or the other. So that means the mechanisms are very complex. It's not just one mechanism, so it's a combination of mechanisms are observed in a material. So how to evaluate susceptibility of this of a material? So depending on the service environment and the steel type, they expose to different, they subject to different tests. So in case of there are some low alloy steels where pipeline material, they run they actually carry hydrogen sulfide. So for this material, they just take a piece of material and then immerse it in the H2S solution without applying any external stress. So and then understand if there is any crack. If the pipe is made of, if it is a seam pipe, that means it has got a they make this pipe using welding by so in that case they need to make a different strategy to expose both body material and weld to see if just in the presence of H2S due to hydrogen blistering it forms crack or not, it forms any blister or crack. The second one is constant load or displacement test. So this is used for measuring subcritical cracking and also threshold crack driving force, which is K1H threshold. This is the minimum crack tip stress field required to start the crack propagating, begin the crack propagating. So, and also, the for accelerated testing, this one will take a lot of time, and this is again they expose it to a certain amount of period depending on the severity they need. In slow strain rate, it is an accelerated test. So it's very easy. That's why the most industry people prefer this to get a quick, at least for in case in the screening stage. That means ranking, when they have a lot of materials in their wish list, then they will test it quickly and then find out which one is better than rank them, and then go to the next stage of selection of materials. So, and then the most concrete parameter to get is fracture toughness test. Again, this is also very valuable test for life prediction stuff. And fracture toughness, as I told, this is the ability to evaluate the ability of the material to do unstable cracking in the presence of hydrogen. And there are several fracture parameters like K1C, J1C, and then critical crack tip opening displacement. They are all very, they are standardized and they're more or less considered as a property of the material, but it's not. They also subject to a lot of variability. So, and then the last one, if the component undergoes fatigue, cyclic loading in hydrogen, then fatigue crack growth is important. I'm going to show some susceptibility measures. So in different tests, what kind of information we get. So most often in hydrogen embrittlement susceptibility evaluation, they use notched specimens, because the most key thing is the hydrogen gets accumulated at the crack tip, and that sustains crack growth. So here, the constant load or stress test, they do several tests, each loaded to different stresses So that's what they call it as applied stress, and find out how long it took to fail. So time to failure. So if you apply, as expected, if you apply certain low stress level, and beyond which it is always the time to failure is the same. That's what it shows. And in the slow strain rate test, here again it's on a notched specimen. The lower the strain rate, lower the fracture stress. That means you need very low stress. It will only sustain very low stress level. So this, that means the strain rate is important. That dictates the mobility of hydrogen and stuff. And then constant load or stress test. This is again using a fracture mechanics specimen. So this is actually crack velocity as a function of stress intensity factor, and this is the threshold stress. This rises up, the crack velocity rises quickly and then plateaus. So what it does is, this is this constant crack velocity regime was more typically used to evaluate the life of a component. Since K is a similitude parameter, which we can transform the value, this crack velocity measured in a small specimen, and if this K is applied in a large component, still they expect the crack velocity to be the same. That's the power of similitude, because most of these large components cannot be tested because test facilities will not have ability to handle it. So there it comes as a boon. So they use this for life prediction and stuff. Fatigue crack growth rate test. Again, this is a crack growth rate as a function of stress intensity factor range. It's it's a range because it's a difference between that sinusoidal wave, max and min. So this is the crack growth rate, the typical sigmoidal curve in A. And in the presence of hydrogen, it just goes several orders of magnitude. The crack growth rate increases throughout the entire regime, including threshold and in the Paris region, and also this is expected to be more or less same, but I think they show it like that. So next, so those are the testing and susceptibility measures. Moving on to mitigation strategies. Here, actually, I referred I just populated the mitigation strategy for steel. So this was actually done by one of the review papers of Harry Bodesia. Here he says, there are about 4 different strategies one can follow to reduce the embrittling effects. So one is coating, to just restrict the entry of hydrogen. So that's one way. And irreversible trap. That means they can have, they can use substitutional atom or some defects carbides nitrides in the matrix. So they will just absorb the hydrogen, not release. So because the reason is, hydrogen that is just freely moving in the matrix is only creating the cracking problem. So but yeah, sometimes these also become a problem, but one time, such as the welding or electroplating, where you have one-time exposure to hydrogen, these things will absorb the hydrogen, and then the material will function as as usual, as normal. And then there are other similar sort of the irreversible traps. Absorbers is, again, they are all strong traps. They just absorb hydrogen, they never release. Only at very high temperature they release hydrogen. So structural tortuosity, they introduce low diffusivity phases in ferrite. Ferrite is a BCC, so it will have high diffusivity. They just they just design the alloy in such a way that the diffusion is not taking place continuously. So they create a kind of a mess create a kind of a maze, which will not allow the diffusion to happen as needed. So it will not allow hydrogen to go to the crack tip and cause failure. So here I listed some challenges. So as I told, some of the fracture. So for hydrogen embrittlement, fracture mechanics specimens are quite useful, but industry looks for ranking purpose. Industry looks for simple, accelerated, and reliable mechanical test for evaluating hydrogen embrittlement of high strength alloys. So this is, I think a good challenge, because people know that it is fracture mechanics specimens are useful, but still they use low strain rate test smooth specimen, and because of its simplicity, and not every place will not have sophisticated testing machines and characterization machines. So, and then the second is dislocation dynamics of hydrogen. So embrittlement happens because of the interaction between hydrogen and dislocations. So that's very important research to conduct, because we don't know really what happens actually in terms of how hydrogen affect the crack tip stress field. Development of in situ hydrogen monitor. Yeah, this is one key instrument which we can use it to measure the hydrogen in the material or the surface, whether it is below the critical, and so that we can operate it. So one can use it as a condition monitoring. So once it reaches some critical level, for example, in steel, they, I'm not sure about this, but they just heat the material, and so when they heat the material to certain temperature, like 250 degrees centigrade, the hydrogen all released, and then the material will behave like a normal material, unless there is no phase transformation stuff. So that's one area to look at for condition monitoring. Spatial visualization, where hydrogen goes and settles in the microstructure. That's for metallurgical point of view. And alloy design, as I told, the low cost alternative or cost effective alternative for stainless steel for hydrogen storage. So in summary, hydrogen damage is a widespread degradation mechanism of engineering alloys in wide. We saw that it's seen in a wide variety of industries. And then the mechanism and the factors affecting hydrogen embrittlement. One key important thing to remember is this hydrogen embrittlement occurs only when hydrogen mobility of the hydrogen is very close to the mobility of dislocation. If the hydrogen is not moving with the dislocations, it's not going to create any kind of problem, because when dislocation moves and hits the obstruction at high velocity in the presence of hydrogen, it's going to create stresses. If they are not coupled, then they are going to be the effects are minimum. So therefore it is dependent on temperature and strain rate. That's the key to remember. And then of course fracture mechanics specimens are useful, but some new methods, simple methods are always sought after. And then we came to the second part. I think I took some lot of time. I think we came to the second part of the talk.
Nagar,
Yes, sir.
a little more voice, please. Slightly it is
Okay.
dislocated. I mean, now it's comfortable.
Okay, brilliant. So thanks. Here I'm going to go through the results of quantitative fractography. This work was actually part of the research we carried out at BPI CAM, University of Manchester. So the aim of the project was to develop hydrogen-resistant nickel alloys. So nickel alloys are actually here I mean super alloys, which is actually has got the major elements are nickel, and then iron, and also niobium, aluminum, titanium. These are two just So super alloys are basically precipitation hardened alloys. Very expensive, but they are good for corrosion application, where corrosion is a process where it leads to one depending on the potential, it leads to rust formation or hydrogen generation. So here the as I told, the driving force here was because of that expensive tubing hanger failure, which actually incur production loss and also repair costs, which no longer they can handle. So alternatives, 708, nickel alloy 708 is actually workhorse material. They make gas turbine engines using this material. That is an alternative, because 725 shown it is failing when they made a box connector. So, and also there was a new alloy composition specially made for oil and gas application where there is no grain boundary phases. So we looked at these two alloys in this project, and also we did a small work on other alloy as well, and I'm going to show that as well. So in this segment, I'm going to evaluate what is the validity of slow strain rate test methodology to measure hydrogen embrittlement susceptibility, because the cracking is main important thing. So we need to use fracture mechanics specimens, but the industries use slow strain rate test. So we are going to show why we should move for fracture mechanics specimen. So first we did a couple of slow strain rate tests. That's basically a simple tensile test, but at a very low strain rate, like 10⁻⁶ per second. So, and then what we are going to look at is use FRASTA, which is a quantitative fractography technique to identify the crackinization stress and local fracture toughness. So as I told, nickel alloy 708 is a precipitation hardened alloy. Actually, it has got gamma prime, which is actually combination of Ni3 AL or Ni3 Ti. And the major strengthening comes from gamma double prime, which is Ni3Nb, so niobium, which is in the matrix. Here I am showing the scanning electron microscope image. So they call it as here I'm calling this as overaged. Why? Because some of this gamma double prime, these are metastable, and they transform into delta phase, which decorate the grain boundaries. Actually, a lot of these grain boundaries have got delta phase, which is actually when the hydrogen goes there, it promotes both combination of mechanisms. The decohesion as well as localized plasticity, and leads to intergranular cracking. So they are prone to hydrogen embrittlement, but still so it's better than 725. So, and we have this new alloy, which is again precipitation hardened using gamma prime and gamma double prime, but no delta phase. Because they found that that's detrimental, but so they tried to design in a way that it doesn't have delta phase. So that's what they reduced niobium, which is actually forming delta phase. And then here, this alloy, this microstructure is a P cage. That means, okay, before that, okay, what is precipitation hardening? That is actually a strengthening mechanism. So thereby, they rely on fine precipitates like gamma prime and gamma double prime. When the dislocation or the moving dislocations actually causes the plasticity. So, but these precipitate stops them, and so when they are stopping, that means the amount of load required to cut the precipitate or just form a loop, they call Voravan looping. So that means we need to apply more stress, more load to get away from the precipitate. So thereby it increases the strength of the material. So P caged is one particular size of the precipitate at which the material attains its highest strength. So this is a P-caged microstructure. You can see there is a big grains and no grain boundary precipitates, which is yeah, they made for oil and gas. And then the experiment I'm showing here, I'm just going to, okay. So what we did was we used this cylindrical specimen actually based on a NACE standard. So that's the standard for conducting slow strain rate test. So test protocol, hydrogen pre-charging, that means it just use three electrode system to do the have electrochemical reaction generating hydrogen on the surface. So we apply a cathodic current density of 7.7 milliamps per centimeter square. So it's a constant current density based on the surface area exposed and at a temperature of 80 degrees for 7 days. Since nickel alloy is FCC face-centered cubic material, so it will have low diffusivity. Even after 7 days, we have this diameter of 3.81 millimeters, and it will reach only the annular radii of about 200 micron roughly. So it takes longer. That's the reason why they think that these are good material for hydrogen service, but still they are not. They are have its own problems. And then did the in situ hydrogen charging, and then conduct the tensile. That means while conducting the slow strain rate tensile test, simultaneously charge the sample with hydrogen. So this is the experimental setup. So we have this pull rod and mount the electrochemical chamber around the tensile. Actually, that's actually subsize tensile slow strain rate tensile specimen, and we have the recirculation pump to provide deaerated sodium chloride solution. So yeah, this is the experimental setup. Yeah, here we have three electrode system to effect hydrogen generation. And again, the response, slow strain rate test, SSRT response of 945X and 718. Here we see that as I said, the P cage will have high strength. So 945X has got high strength compared to 718, which is the red curve. And for 945X, in the presence of hydrogen, it fractured very close to the yield point. And in case of 718, which is slightly higher ductility, you have higher elongation, but at the same time, it in the presence of hydrogen, it showed higher ductility compared to 945X. So this is what we get from slow strain rate test. And the fractography, so I'm going to compare how it looks in air and how it looked for 945X and 718. So in air, it is typical dimple fracture, and ductile void coalescence mechanism. 945X, see, in this case, the reduction of area is huge, but here it is very, very minimum. There was no change in the cross section due to necking. Here also, we can see that flat facets, originating from cleavage or twin boundary cracking. And in 718, it actually in the outer, as I told, here the outer region alone has got a lot of hydrogen, and also during the in situ test, some more hydrogen is pumped in, so we get this kind of a ring. And in 718, we don't have it, that kind of ring. It's just skewed, but it showed a mix of cleavage. That means transgranular and intragranular ring. Trans in the sense it will just cut through the grain, and intragranular, it's cracking through the grain boundary. So here comes the quantitative fractography, crack initiation. So we are going to find the crack initiation point using fracture surface topography analysis. This is the main bit of this study. So what we did, this was done in 90s. They used surface topography to replay or reenact the fracture event. So what we did was take the topography of the material of the fractured surface, complementing surfaces, and pull one surface, fix one, and then pull one below that, so that it simulate the cracked state. Sorry, not no crack state, and then lift the EFS2 in this case, move it upward in steps, so that we get, and then we see the connection between them. When the points on the surface, if it is above the fixed one, that will be marked white, and those which are below the fixed surface, points that are below the fixed surface, they will be marked black. So we'll get a binary image, which is called as fractured area projection plot. So that will give, so this is what the procedure is explained here. So this is what we use to see how the crack evolution of crack occurs from the topography. So here I'm going to show the video. So okay, so this is the slow strain rate test, and we have got a crack, then fractured, and we use these are the complementary fracture surfaces. Use confocal microscope, which will give the depth data. That's what we call topography, and these are the topographs of the complementing surfaces. And this is the separation distance. So if FS2 is brought down and moved up slowly, so at the minute it is, so now partially cracked, it is moving up. So some places we see that it is coming out. So now it's fractured. So we use this in small steps, and to get the crack evolution in multiple steps. Now in a minute we'll see that crack starts to initiate there, and that's the initiation point, and it starts to grow in. We tend to see that it grows faster at the outer surface than in the central region. So so now the crack starts to go around the sample where the hydrogen is present in abundance. When the central region, it was only no hydrogen at all. So that's the one to go lost. So this is a simple animation to show that how it was performed, and finally we get this series of fracture. This one fractured area projection plots. So we'll go to next slide. So here, so we know that we displace in by a small value, like in this case 0.05 millimeters each time. And by doing this, this is a uniaxial test, and we know how much displacement needed to fracture it from the point of crack initiation. So what we did was we subtracted, from the stress strain curve. So this is actually, converted into elongation, and then backtrack, and then come down, and then see that, where crack initiated. So the third fracture area projection plot corresponds to this area where crack initiated. So what it tells is we have the crack initiated, in the elastic region of the stress strain curve. So this is for 945X. This is, it's just frailed in a brittle way. And for 708, we did the same exercise and found that the crack initiation occurred at after yielding. So that means it showed a lot of plasticity before crack initiated. So yeah, that's how we differentiate and find. We use that technique to differentiate what when the crack initiates, and it's not. So that means it's not. It's not a simple tensile test where we have to expect continuous homogeneous deformation and then no cracking neck and then fail. So but it is not that way. We have got crack. That's why people say it's fracture mechanics test. And here we did a clever experiment using different alloy where we just, this is the gauge section of the specimen, and then we just masked the entire gauge area except a small window which is exposed to hydrogen. And what we saw was the crack grew like a crescent. So yeah, this is very interesting, and that means the analysis we do is in fact showing the correct expected result. So, and also we backed up using acoustic emission, which monitors the noise created in the process of cracking. So what happened was, this is the place where the crack initiation, when we found that using FRASTA. In acoustic emission, they also detected crack initiation noise at this point. So it is very well validating the findings of FRASTA. And also we used simultaneously we also measured we videographed the test, the entire test. So, and what happened was the crack didn't appear until the very last point at which just the load fell off precipitously. So, and as I told, here you can see that this is the shiny specimen as as fresh as it is. Yeah, and then you can see the hydrogen bubble generating on the surface, which yeah, that's the case. Not all hydrogen produced on the surface gets into the material. Only a small fraction of it gets in. So, but still, that's very virulent to cause the damage. Yes. So, and then we have this finite element simulation as well, but it is also off by some factor. Yeah, but I think the most important one, the experimental validation, is from acoustic emission, which guarantee which validates the findings of FRASTA. So, what are the implications? So, early crack initiation and subcritical cracking is observed in slow strain rate test, which is not better way of evaluating the susceptibility. So we need to go for fracture mechanics based test. And also fracture toughness is we did some fracture toughness test and compared with the results from SSRT for ranking purpose, and for certain heat treatments it wasn't we didn't see the same order of ranking. So that's the message. We need to use fracture mechanics, but I think we can also use this FRASTA technique to complement the result. Again, we use the topography to measure the local fracture toughness, which is, again, as I told, it's the measure of driving force required for unstable cracking. So we used the crack tip opening, but yeah, we from some distance from the behind the crack tip. In one case, 0.05 and 0.1 millimeters. So this thing needs to be some more research is required to find out how much distance at which we need to measure. But yeah, mostly it is actually to have this 45-degree to meet this criteria. So this is the formula. K is a square root of Young's modulus flow stress times tip opening. So we selected, we did that for 945X and 718. So these are some details. And these are the cross-sectional, plots where, we see that the crack is growing This line analysis shows that the crack opening with when this one surface is moved with respect to the other, and also I just plotted the local fracture toughness for each separation distance. So when we did for the entire surface area of 945X and 718, we get the some kind of normal distribution. We'll see that in a minute. Here for 718, for 945X, we saw a very sharp crack, and for 718, we saw a tortuous crack. That means we have a lot of resistance to crack growth, because the load applied will be consumed in in the interaction between the surface wake, the crack wake. So and then we to get some confirmation, and we measured the crack tip opening displacement at the surface of the surface cracks on this specimen. And then this is the crack tip, and we measured at 0.05 millimeters and 0.1 millimeters, and we got this, and then plugged in that value into the equation for K, stress in local fracture toughness, and we got something like this. 945X was slightly lower than 718, but this is a one-off measurement. This is just single measurement we did for the entire surface area using the topography. We got for 945X. Actually, these are blue one is for 0.05 millimeters behind the crack tip, and 0.1 for this brown color bar chart histogram. So here we can see that and then this is for 718. For 945X, the spread is very narrow, and for 718 it is slightly broadened. And also in the highest value, in this range, it's about it's actually wavering around 80 and 120. But for 945X, it's pretty low, even if we consider 0.1. So in general, what it shows is 945X has got the fracture toughness is reduced a lot compared to 718. But we need to remember the 945X is especially made for oil and gas purpose. But the thing is, they tried to fix one problem by eliminating grain boundary precipitation, but the failure mechanism is completely different. It was mostly cleavage and twin boundary cracking. So that's the problem with hydrogen embrittlement. There are several combination of mechanisms operate simultaneously. We need to carefully find strike a balance to get a better alloy. So what this tells us is, of course, the SSRT shows loss of ductility, but there are some gaps which we need to address. And FRASTA, fracture surface topography analysis is helpful to identify, to do some postmortem analysis. It's a technique, can reliably do the can be used to do fracture replay analysis with using topography of the fracture surfaces. And also we can get to see the local fracture toughness between different alloys. So that's a pretty useful thing to do. We can also understand the effect of microstructure locally. We can bring a correlation and understand the microstructural issues. Challenges. So in FRASTA, so we had done this simulation using uniaxial displacement. What if the surfaces undergo torsion, combination of bending and torsion and stuff like that? So that's we need to develop that's a scope for developing a methodology to do that. How to implement FRASTA for those kind of situations. Secondly, we can as I showed, the crack fronts are very easily obtained from the fracture area projection plot. Can we use that to find, we found local fracture toughness. Can we use that crack front and use finite element analysis to get the to determine global fracture parameters like K1C, J1C, CTOD, critical CTOD. So that's another challenge, for someone interested. I think I took a lot of time, I think. So acknowledgements. So yeah, I want to thank the University of Manchester for the facilities, BPI Camp for funding, and also my colleagues for technical discussion. And also special thanks to the organizing committee, all professors, particularly Professor Ramesh there. So yeah, I thank very much for giving this opportunity to present my understanding. Thank you, sirs. If you have any questions, please raise your questions. Thanks.
Thank you for the very nice presentation, Dr. Dinagaran sir. Thank you very much for your valuable inputs, and many things were clarified related to this failure form. And there are a few questions from participants. I wanted to represent the same on behalf of them. The first one is the slow strain rate testing done to measure the hydrogen embrittlement. Will it be a costly test?
No, actually, it is. Relatively, it is cheaper compared to fracture mechanics test because of the specimen preparation. We need to have a notch, and also, we need a specialized testing machine to do that, and also accessories. So slow strain rate is a relatively economical and also easy to do test.
Okay. Nice, sir. There is one more question. What is the difference between two nickel alloys you referred, sir, in your presentation? What is the difference here? They're asking nickel alloy.
Okay, that's a good question. So as I told, 708 is it's a workhorse material. That means they use that since its discovery in several industries. So that's both are precipitation hardened material. 708 is a workhorse material built for aerospace, but they modified it for oil and gas slightly. But still, it is having problems. They are not, they're doing okay, but they wanted to go for higher strength as well as good resistance, which they were not able to achieve. So they went for a new material to and avoid all the complications, all the failure lessons. But still, 945X was not doing its best. So the difference is they reduced the chemistry. So they reduced the niobium content in 945X to get to not to have grain boundary precipitation. That is the delta phase, which is not good for hydrogen embrittlement.
Okay. Nice, sir. And last one from my side. There are other questions from YouTube live stream, it seems.
Okay, sir.
I will represent the other one.
Yes, sir.
What is intergranular failure, and in what way, what is the possibility for hydrogen embrittlement situation? Will it be intergranular?
Yes. Okay, that's a good question. Yes, as I told, intergranular is actually when we have deleterious phases at the grain boundary. Naturally, the grain boundary is full of, it will occupy a lot of hydrogen, and in the presence of these, trapping phases, so it will elevate the hydrogen concentration at the grain boundary, which results in intergranular fracture.
Okay.
But there are certain situations like in 945X, the grain boundary is clean and nice, but other features are actually weaker than grain boundary. So we see cleavage or twin boundary cracking. So both are seen. That's what my answer is, both.
Oh, okay, sir.
Depending on the alloy.
Okay. Dr. Sandamari sir, do you want to represent any questions related, from other live stream session? No? Sir?
Sir, Ramesh sir, I think some other questions also available in the chat box.
Oh, yes, sir. Dr. Sandamari or any other?
Can I read, Ramesh sir?
Yes, sir. Yes, sir. Yes, sir. Then it is little slow for me to open.
Yeah, here one question is from Dr. Kishore Kumar. Kindly brief about microstructural analysis before and after HE for 718 and 945 X alloy.
Okay. So it's about the microstructure. Yeah. So here, the overaged. So I think I'm going to go again. So here, this 708 has got gamma prime and gamma double prime precipitates. The major strengthening is coming from gamma double prime. They are of the size of hundreds of nanometers, sometimes even less. If it is in overaged condition, we saw something around 80 nanometers gamma double prime on the average. And also this has got delta phase at the grain boundary. So this insert here, I'm showing this, it's on the boundary they have delta phase, which is actually deleterious. But still, this is a softer matrix. That's the reason why 718 is better than 945X. And 945X is a peak-aged, slightly bigger grains, and they have large fraction of and also long twin boundaries. So that is also one reason why we see twin boundary cracking in 945X. Is that does that answer?
Yes,
Question?
Yes, sir. Yes, sir.
yes.
Okay.
There is one more question, perhaps Dr. Puviyarasan from PIT, Particular Engineering College. He asked, is there any specific way to investigate hydrogen diffusion in additive manufactured materials?
Yes. For mesh. Yes, sir. Is that?
Shall I read the question again, sir?
Yeah, I think if I get it right, the question was about measurement of hydrogen diffusivity in additive manufactured alloys. Is that
Yes,
right?
sir. Yes, sir.
Okay, thanks. Thank you, sir. So yes, actually, there is a well-established test method for measuring hydrogen diffusivity. There are a couple of methods. One is hydrogen permeation test. So where they have two electrochemical cells on either side of thin material of your choice. So in your case, you're going to use additively manufactured specimen. So the hydrogen permeation test can get you hydrogen diffusivity. And also there is another technique, thermal desorption method. So that will also, so in that case, first we need to charge the material with hydrogen and then heat it up to different temperature, the temperature range until all hydrogen comes out of the material. So you will get to see the diffusivity as well as binding energy and those kind of parameters. So you'll get the transport properties of the material. Thanks
Hello,
for the
sir.
question.
Yes,
Sir,
sir.
there are some questions from YouTube also.
Okay.
Yes, sir.
Yes, sir. From Chandrasekharan, sir. In chemical plants, most of the pipes are using PTFE lined pipe. Inside coated with lined material. There are limitations. Any modification, field weld is not possible for length adjustment.
Okay. Yeah, I think that's the issue. Yeah, they do PTFE coating to protect the material from corrosive action. But that's a kind of repair work if they wanted to extend the pipe. they need to recoat or something like that. But yeah, but I don't have deep understanding of that issue.
Okay, sir. Thank you, sir.
Thank you.
Another,
Yeah, thank you.
another question. To restrict the hydrogen trapping, what may be the probable coating thickness, or how to define the coating thickness to prevent the hydrogen trapping?
Yeah, I think that's again, one should understand the diffusivity of the coating material. Yes, we can use the hydrogen permeation technique or similar technique to measure the diffusivity of the coating, and then based on which one should decide, and also how long it has to come, what is the life expected. So based on which one can derive the thickness required. So yeah, here you can see that for steel they can go for nickel, cadmium, because these are going to delay the hydrogen diffusion.
Okay, sir. Thank you, sir. Another question.
Yes, sir.
The Inconel 718 fabricated by additive manufacturing subjected to HE. Hydrogen embrittlement, subjected to hydrogen embrittlement.
Okay, so the question is the effect of hydrogen on additively manufactured 718. Is that right?
Yes, sir. Yes, sir.
Okay. Yeah, that's a good question. I think. I don't have idea about it, but I think the understanding of the conventionally produced 718. I think we'll have all the issues that we have with 718. Probably that may mitigate. But additive manufacturing, as far as I understand, they have the layers from the solidification layers, which is the artifact of additively manufactured. That might have some issues. I think I'm not sure about it, but I think all the issues that we have with 718 maybe there in additively manufactured 718 as well, but I'm not sure.
Sir, another question. Please brief about fractography analysis of isotropic and anisotropic materials.
Okay, right. So yeah, I think I think the question might what I'm trying to understand is the question might be trying to understand is it related to the frustra, because nickel is an anisotropic material, and it could have an effect on the way we measure the crack opening displacement and the local fracture toughness, because the E value, which is the Young's modulus, which is also dependent on the direction of the material. So that's one thing to think about. How to incorporate anisotropy effects in in the formulation of local fracture toughness.
Someone asked what is frustra?
Okay, that's fracture surface topography analysis that was developed by a group in in the US. So in the current analysis, what we did was that we used that methodology, and we advanced it by including the crack initiation measurement.
Yes, sir. The last question is there any remedial measures for hydrogen embrittlement, like coating or alloying?
Yes. So yeah, as we are seeing on this slide, there are these are like for service. Hydrogen generated during service could be avoided by having coatings. But for one-time hydrogen ingress, traps could be these kind of microstructural design could help.
Yes, sir, that's all the question was, sir. Thank you very much, sir.
Okay,
Now I
thank you.
request
Thanks for.
Kripagaran, sir. Yes, sir. Kripagaran, Assistant Professor, to deliver the vote of thanks.
Good evening to all present here. I would like to thank our honorable speaker, Dr. Dinagar Sambat, project leader, fracture and fatigue metallurgist, research and development, Lotto Steel, United Kingdom, for making an excellent presentation and making this webinar a very meaningful and interesting. I would like to express our deep gratitude to the SVCE management. I would also thank our beloved principal, Dr. S. Ganesh Vaidyanathan, sir. I would also thank our beloved HOD, Dr. H. Ramesh Babu, sir, for his guidance and his moral support. I would also like to thank these webinar coordinators, Dr. R. Ramesh, Dr. C. Sindhamari Kannan, Mr. J. Sivaram Pandian, and myself. I would also thank to Mr. Kumar Swami, sir, for his support for YouTube live streaming for this webinar session. I also extend our sincere thanks to participants for their active participation and attention. Finally, I also thank all our department faculty members for their encouragement and support in making this webinar successful. Thank you all.
Thank you, sir. Thank you, sir.
Thank you, Dr. Dinagar Sambat. Very interesting interactive session.
Yeah.
We learned many good contents belonging to many hydrogen embrittlement theories. Yeah, very kind of you.
Yeah.
And we had enjoyed your session a lot.
Okay, thanks.
Yeah.
Thanks to hear that. And also you had a very big audience, and I think the questions were very meaningful, and also something to think about. Some questions are related to additively manufactured 718. I think that's the emerging material. So that's pretty good questions from the audience as well. And thanks again to the organizing committee of mechanical engineering for this webinar invite.
Thank you. Please kindly hold on. Announcement to participants. The feedback link is posted in your chat box. I kindly request you to fill the same. The certificate of participation will be sent to you within 2 days. This will be sent to your registered mail ID, and kindly access it. Thank you all.